So thank you all for joining us today. This is for our February TRX webinar presentation. This is the first one of 2026, and we're hoping to have a pretty strong list of presenters throughout the rest of this year. So to go ahead and kick things off, we're going to have Quintus Technologies presenting, and our presenter is Jackson Hise. Jackson has his master's in material science from The Ohio State University, as well as a bachelor's of science in mechanical engineering. During his academic career, he had gained research experience at Ohio State, as well as the Naval Research Lab, and has a focus on solid-state transportation and works as an applications engineer at Quintus Technologies. So Jackson's going to go ahead and present, and throughout the presentation, there are two ways that I would ask that you ask questions, and that is through the chat function and the Q&A function in the Teams system. So with that, I'm going to hand it over to Jackson and let you take it away.
Perfect. Sounds good. Well, thank you everyone for being here. Today I'm presenting on additive manufactured integrity. I'm presenting with Dwayne Arola, a professor of material science at the University of Washington. I know Chad Beamer was slated to be here. Unfortunately, he cannot. So hopefully, if you're here to see him, I can carry along this conversation. Just to give a quick outline of the webinar, I'm going to go over the HIP fundamentals and benefits. Then we'll talk about recent advancements in HIP equipment. This is really with the push to discuss modern HIP equipment so that we can therefore have a conversation about trends in additive manufacturing and what this modern equipment can do. Then for the second half, Dwayne will be presenting on a round-robin program in powder bed fusion TIE-6-4 and variability understanding within that. So with that, let's go ahead and get started. So just a background on Quintus Technologies. Quintus Technologies' work revolves around isostatic pressing. The only real difference as an equipment manufacturer is what medium we're applying to the vessel in order to pressurize our parts. So of course, we're going to be talking about hot isostatic pressing here in this presentation. We're using argon often as the medium, and we're applying a temperature up to 2000 degrees C on our material with 200 megapascal maximum. Quintus also develops work on warm isostatic presses, which is a growing industry within solid-state batteries, where oil is used to densify the material, reduce interfacial resistance between our cathode and anode, and is certainly growing. Lastly, and I won't talk about it very much, but probably the most interesting thing I think here at Quintus is its cold isostatic pressing, which is used in the food and beverage industry. Here we're taking bottled product, we're putting it within a cold isostatic press, pressurizing it, and actually disrupting the cell membrane so that bad bacteria cannot reproduce. I, of course, have no understanding of what really is going on here, except that if you ever see cold isostatic pressed, it wasn't some nice hand press. It probably was industrial equipment. With that to discuss a quick background on Quintus, I just want to point out Quintus has developed uniform rapid cooling and then uniform rapid quenching. Really, as a equipment manufacturer, we're pushing the field along on what we can do within the HIP system. This leads to what I'll discuss at the end of my part of the presentation on high pressure heat treatment. So of the products Quintus builds, we have first our R&D and small production units, but then this scales to our mid-sized and large production units. The value of this is really that we can reproduce anything in a small system that we can do in a large system. And specifically, if you're interested in hipping material, what may fit into a small system can also undergo the same performance parameters in our medium and large size units. And so if you want to hip with the build plate, say, Quintus has products that can accommodate that. Looking quickly at the fundamentals of HIP, if you're unfamiliar, hipping revolves around applying temperature and pressure. So our temperatures are going up to 2000 degrees Celsius, but this is really material dependent. Here we're looking at only about 80% of the material solidus temperature. We're also applying pressures up to 200 MPa, and the first and foremost use of HIP is to densify solids. We see that in traditional cast variants, hipping has been used on mission critical components for many decades. Here we're applying our temperature and pressure around our part, and given that there's a gas-tight surface, we're able to decrease that porosity and fully densify our material. We also see a growing interest in the consolidation of powder, where we create a can, a near net shaped can to the component we want to create. Then we fill it with powder, pulling a vacuum on this and then placing it within the hip. We can get a single uniform piece of material. This is significant because it rivals traditional forging, except that the cycle time, the process time, the manufacturing time is significantly decreased compared to those forging operations. If we want to think about just the quick material science, I know Dwayne will get into more of this. Densification mechanisms first go through mechanical deformation, where we have the defects collapsing because of this applied pressure. And then over time, over our hold, we have creep and diffusion, where we're seeing that these collapsed defects are bonding. I discussed the densification of products. I can discuss the consolidation of powder, but there's other operations that can be formed in the hip, such as diffusion bonding, where we're joining two dissimilar materials together in solid state. We also have this high pressure heat treatment, which is a development that's only capable with the modern hip system that I will be discussing later, but essentially is doing the heat treatment cycles within the hip after applying this high pressure parameter. So if we want to take a step back and just look at some broad overall advantages of hip material, first and foremost, hipping the material eliminates internal defects. This elimination of stress concentration and crack initiation points lead to superior mechanical property. If we want to take an extreme example, we can see this machined artificial pore here. Here we machined an 1-inch diameter pore into the component, then welded these two parts together. After we hip, we see that we fully resolved and healed this hole or this pore within the material. The only true challenge here would just be getting that gas-tight structure in which the applied pressure medium cannot penetrate the material and allow for the pore not to be healed. If we're looking at additive manufacturing variants, we can see that powder bed fusion, DED, and binder jet all have a reduce or elimination of internal defects after hipping. And this really provides value we'll see here in a second on what it means for printing parameters if we're going to also hip. So I spoke to the elimination of internal defects, but this really produces superior material properties. We see that hipped materials have dramatically increased fatigue life, up to 100 times, increased ductility and fracture toughness, and better creep properties. If we're thinking of something like GRX 810, a recent ODS alloy that came out of NASA, we see that the hipped version has a creep value 2 times as large as the printed use case. We also can think of reduced property scatter. Here we know that there's natural variation of defects between components being built. One example in the additive world is even among the single build plate, variations across the build plate produce different defect locations. So here we can see sample 27, sample 35, and 46, and where these defects are scattered throughout the part. By hipping this, we can resolve these internal defects, providing not only a fully dense sample, but also predictable variation between each and every component. Lastly, improved machine polished and surface quality. This, of course, increases corrosion resistance, improves sealing performance, but really goes down to this internal subsurface porosity. Here we have a printed part. If we were just going to chemically clean it, we would see that there's subsurface porosity that's exposed by pulling away material. But if we hip and resolve this porosity, then we can chem clean and get a nice uniform surface, which therefore increases things like corrosion resistance. Now to discuss modern hip equipment and really some capabilities within the machines that can produce interesting value to a user. First, Quintus hips use a wire-wound pressure vessel. This is where we have a small vessel frame and then wind it with miles and miles of material or of wire. By doing this, we're able to integrate controlled cooling channels, leading to controlled and steered cooling rates. The alternative to doing this, which Quintus does not do, is a monoblock system which relies on natural cooling to cool down the system in the furnace and contained. We also at Quintus here have forced convection, which uses fans and injectors at the base of the vessel to circulate gas flow within the system. This leads to the mixing of hot and cold gases, leading to temperature uniformity and temperature control. Really, the value of these two equipment features is first forced convection heating. So here we have improved temperature uniformity, reduced process cycle time, and lower energy consumption. This is because we can steer the coolant or the heating of the system to the desired rate, hold it, and then cool. And of course, if we can do this quicker and more efficiently, there'll therefore be more cycles we can implement in a given time. Quintus also has uniform rapid cooling and uniform rapid quenching capabilities. The quenching technique used within a Quintus system has a cooling rate faster than that of an oil quench, slower than that of water quench. So here we can quench and cool the system significantly quicker than conventional cooling, which allows again for that reduced process cycle time, but also the opportunity to use high pressure heat treatment that I will discuss here in a minute. Finally, if anyone has ever dealt with hipping Ti-6-4, you know that the material is prone to oxidation and alpha casing when it undergoes the HIP cycle. Quintus has developed something called Quintus Purus, which is a technique used in the HIP cycle to mitigate and remove that initial moisture presence so it cannot react with the parts. We're seeing the use of this in the medical industry, where the materials coming out of the system are already optically viable for use. I've discussed and mentioned it a couple times, but just to touch base one more time, high pressure heat treatment is really of interest here in these modern Quintus HIP systems. We know that traditional conventional heat treating methods first do a stress relief, then you HIP, then you solution heat treat, and then you age. But given that Quintus HIP is capable of controlled cooling and that uniform rapid quenching, we can do all of this heat treatment within one equipment, one piece of machinery, which is a hot isostatic press. So here we have our stress relief and HIP, then combined with the solution heat treatment that comes from the quenching capability, as well as an age. This, of course, would reduce the number of process steps, reduce total cycle time, improve process and quality control. And one thing to note is this is being commercially applied today, specifically for aluminum alloys that we'll see here in a minute. So I discussed these modern HIP systems, but want to point out that it's not only theory, but there's multiple places throughout the US that are taking advantage of modern HIP capabilities. Not only are the companies listed here using these modern HIPs, but many other companies that aren't mentioned are taking advantage of the value that comes with a new and optimized system. I wanted to quickly point out how Quintus has a HIP application center. I'm sure if you're here for Chad, you would recognize Chad in the picture, but Chad and I work within a application center in Columbus, Ohio, that's primary goal is to support the development of HIP processes. So here we evaluate new HIP parameters, we optimize current center and HIP processing, and do proof of concept with potential customers. A lot of the work Chad and I put in is in collaboration with OEMs, universities, and national labs, one of which a university collaboration here at Dwayne is going to be highlighted, trying to develop and advance our HIP capabilities. So just a couple of trends that I'm going to briefly talk to in the additive world before I hand it over to Dwayne to give a case study on this. One trend is the print faster using HIP. I mentioned in an earlier slide that we require a gas-tight structure to then HIP and densify. So as long as our outer layer of the material is fully dense, then the internal parts can be resolved. So this would allow for a print faster using HIP technique where you have a lower energy density or lower hatch spacing, or I guess higher hatch spacing, in order to get the same part at the end. Because even if you have defects due to this higher printing rate, you still hip and resolve them. An extreme example of this is the shelled concept, where the structure was printed on 3 sides, fully dense, but then unprinted powder was left contained. Hipping, of course, shrunk the part, but it did create a fully dense structure of material. Another trend is non-conventional heat treatment. This is really lower temperature, higher pressure than we've seen in the past. So as I mentioned, castings have undergone HIP for many decades, and traditional HIP variants might not apply to the additive type of part. So here, if we're looking at TIE 6.4 or Inconel 718, using these traditional HIP parameters for cast variants, we see that coarsening of our microstructure. Rather than accepting this, there's an optimized opportunity of applying lower temperature, higher pressure to fully densify the material, as well as not coarsen the grains as our traditional HIP parameters do. One thing that's interesting in the last year or two that's came out is standardization of this optimized HIP parameter. SAE AMS is used in the aerospace and high-performance industries, as I'm sure many of you guys know. But AMS 7028 calls out TIE 6.4 laser powder bed fusion components and the HIP process required. This is an alternate to the traditional cast variant, as we have higher pressure, 190 megapascal compared to 100 MPa at 815 degrees C, so that lower temperature. I talked to something that's been standardized, such as TIE 6.4, but there's also plenty of work going on to optimize and develop these optimized parameters for other materials. One of this work is with America Makes ATI 1700, where we're working with Boeing ATI RPM Innovations to accelerate the maturation of the nickel-based superalloy ATI 1700. Here at Quintus, we're taking part in this by utilizing advanced HIP manufacturing strategies in the form of high-pressure heat treatment to optimize the microstructure for our desired outcome. One other thing I want to note and discuss is this high-pressure heat treatment post-processing. We know that, especially in aluminum alloys, AM aluminum alloys in particular, that there's too many post-process techniques. There's distortion during water quench, and there's hydrogen blistering that occurs. Well, if we do all of this under a pressure medium, we're able to mitigate and avoid quite a few of these challenges. We can do the stress relief, HIP, and solution segment all within a Quintus press and do the quench under this argon medium. This alternate approach avoids water quench distortion and also produces acceptable tensile properties. As I mentioned earlier, this isn't only in development being studied, but is actually being applied by some some OEMs developing and using this aluminum alloy. So with that, I want to pass the torch off to Dwayne, who can give a more in-depth case study on what is going on with TIE 6.4.
All right. Thank you, Jackson. That was great. Good morning, everybody, from the beautiful Pacific Northwest. Happy to be here and talk a little bit about the things that we've been doing with respect to application of HIP, but our program is mostly focused on variability. So I want to begin by just making sure that I acknowledge the fact that the case study that I'm going to present is actually part of an ongoing effort that's supported by the FAA. This is supported through what's called the Advanced Materials in Transport Aircraft Structures through the Center of Excellence. And also, I'd like to be able to point out that the work that I'll present is actually the product of contributions of a large number of students that have been engaged in our work. So our program addresses the challenges faced by companies that have adopted laser powder bed fusion and then, of course, seek its application for either stress-critical or safety-critical components. Of concern, of course, is the variability in properties that's going to be exhibited by the metal, for example, in a single component, based on where it's located in the build chamber and its orientation, perhaps. In the case that what we need to do is produce more than one component, now what we've got to do is we've got to consider the fact that there can be variations that arise from the property variation through multiple builds. and make sure then that we can understand the degree of that variation that takes place with regards to evolution in the machine's condition and or process control. And then in the case where we need to recruit additional machines, what we're interested in is to consider the degree of variation that occurs across those machines. Those can be either within our organization or could be, for example, the variability that occurs in machines across organizations or in disparate locations. So in order to be able to address this, typically what we're doing is we're referring to categories of process variability. And so here what I'll do is I'll refer to an intra-build process variability. This refers to the variation in the metal quality and the properties within the build volume of a single machine. Next, we could talk about the inter-build variability, which now accounts for that's within a single machine but over multiple builds, which could occur from degradation of feedstock that occurs from reuse, for example, or again, evolution in the machine condition. The last category of variability refers to that which is between machines. All three of these sources of variability we've got to be able to understand. And of course, they all contribute to the reliability of the metal. So it's key for being able to quantify them and then understand root causes. So just to make sure that it's obvious, the objective of our program overall is to characterize that variability in the microstructure and then mechanical properties of a grade 5 titanium that's produced by laser powder bed fusion. And the purpose is, of course, to be able to advance applications across aerospace with an increase in understanding. The way that we're doing this is we're utilizing a round robin. It's led by the University of Washington. We've got a large number of contributing partners. They're in the aerospace industry primarily. They're conducting prints and then interested or invested in making sure they understand the degree of variability that comes from their machine over the categories that I just described. And then in this case study, what I'm going to be doing is, although our program is focused on both static, cyclic, and then also dynamic properties, I'm going to be referring to the stress life or the finite life fatigue properties that we've been able to examine. And of course, what I'll be doing is highlighting, of course, what we see with regards to the inclusion of a hip treatment. So to make sure that we protect the identity of the participants, what we're doing here is you'll see that I'm going to refer to the round robin partners from a blind format. What they're doing is they're providing metal to us with regards to a condition that we've been outlining that I'm going to refer to in a little bit. So the program structure involves all the partners that we have engaged in this effort are operating an EOS M290. They're all utilizing a single lot of powder, and that means that what we're utilizing is a grade 5 titanium. A large lot was purchased at the beginning of our evaluation, and then our investigation, and then what was done is dispersed portions of that volume to the individual partners so they could utilize it in their machines. We all agreed to follow a single process control document. That took a long time to make everyone agree to that, of course. And all partners are also using the same process parameters. Those happen to be the default parameters for producing components from 6AL4V. All partners also follow the same build design, which I'll introduce in a little bit. So I just point out here the process control document that everybody was working together in order to be able to develop so that we could all agree on the framework of the investigation and the nature of the builds, but also that we knew a lot about the individual machines that were participating within the program. We had a questionnaire that identified the age of the machine, the control software, etc. All details that were important for being able to understand potential sources of variability. So to address the intra-build variability, we utilized a build design that discretizes the build envelope into two levels, as you see here, defined as A and B. And then in each of those levels, you see that we have 5 zones. There's a picture of the build that comes and conforms to that particular discretization on the right. You'll see that we have clusters then of components in the horizontal and then also in the vertical orientation within each of those zones. You also see the labeling from a semi-oblique view here in this picture on the right. For those of you that are familiar with the M290, you know, for example, that the inert gas flow is coming from the back of the machine, so behind zones 1 and 4. And then the recoater blade is moving from the right to the left in this particular configuration across the build plate, which you see at the bottom. Okay. All right. And then for each of those hexagonal rods, what we're doing is sectioning out portions within those individual zones, which we then apply post-processing to. Each of the partners which is involved in the program perform their builds and then send that metal to the University of Washington. Post-processing involves potentially a heat treatment process at the university, utilizing an argon environment for a low temperature anneal. What we'd be doing then also is doing support removal and then, of course, net shape machining, and then recruiting the use of a solution partner in order to be able to do the longitudinal grinding that's required for the fatigue studies, which I'll point out in a little bit. Next thing we're doing is evaluating porosity distribution within the metal, within each of the zones that was produced and for each of the partners. After understanding then microstructure, what we'll do is move on to fatigue, cyclic loading, which I'll describe in just a little bit. And then after we have components that fail, what we're doing is evaluating fracture surface morphology, identifying root cause or the origin. That's done 100% for all our failed components. And then what we'll do is we'll also evaluate microstructure, detail of grain structure, look at chemistry, and then also utilize portions of the powder to be able to examine chemistry of that particular lot of powder within that individual build for the partner. So just to make sure I point out clearly, so our program involves two different forms of heat treatment. One was a stress relief treatment, which was conducted, as you see, at 745 degrees Celsius for 2 hours. Or another portion of that particular lot of metal that was produced by the partner was subjected to hot isostatic pressing. We could compare then properties that come from stress relief and hot isostatic pressing, and then of course understand how that contributes to variability. The HIP process was conducted, as Jackson pointed out, according to the AMS 7028 spec, which is this low temperature, high pressure process. And what I'm doing here is I'm showing you an example of a portion of results from micro CT. So I'm showing you a quarter section of the gauge section of one of our fatigue specimens. So you're looking at the highlighted portion in blue, and you're looking down the axis of the gauge section, comparing then stress relief condition and the HIP treatment. What you're seeing then is the distribution of pores within that microstructure. On the left, of course, you see the specks of blue and green. Looks like a large number of them, but actually, of course, that's because we're integrating those pores that are throughout that particular 30 millimeter length along the gauge section. But nonetheless, the important point is compare that to what you see in the HIP condition. You can see that this is all gray. There's no evidence of pores within this microstructure. We were amazed when we saw this at first. We couldn't believe it. And then I'll show you the other evidence that comes from looking at the fracture surfaces. So I won't be showing any more micro CT results. And the reason is because on the right-hand side, there's nothing really to take a look at that gives us an indication of what's contributing to the performance of the metal. All right, so just to make sure I'm complete about what takes place as a function of those two heat treatments, again, it's either or a stress relief that's conducted in argon or the HIP treatment. We start with, for example, on the left-hand side, the as-built condition. This is our standard Widmanstätten microstructure of acicular grains, alpha and beta ribs. As a function of the stress relief process that's conducted, we get a little bit of coarsening that takes place, and that's exactly the same as we see for the HIP treatment, conducted at a little bit higher temperature, a little bit longer time, so you see a little bit greater amount of coarsening that's present. Right? And that shouldn't worry you. We don't get recrystallization. We only get the annihilation of the smallest portion of the alpha-beta interfaces, and of course then a degree of coarsening that results. All right. So the powder that we're utilizing in the builds for our fatigue program is actually coming from that lot of powder for each of the partners. They built a series of builds for evaluating static properties, and then what happens is that powder was used, topped off to replace that which is consumed in the previous build, and each of the partners then built 4 of those builds that I showed you outlined for the fatigue program. So you're looking at a slightly different oblique view here. Each one of those builds rendered a group of almost 200 specimens in the horizontal and vertical orientations. That was sent to the University of Washington along with a powder sample. So what we could do is track the powder chemistry and introduction of contaminants if it was relevant. Okay. So each partner built nearly a little bit over 700 total specimens. And so after receipt. Again, I talked about the heat treatment and, of course, the net shape processing, which was conducted in order to be able to meet the standard, which is defined by E466. So just for those of you who are fatigue individuals, we performed all of our fatigue testing according to E466. That's cyclic axially loading to failure. We performed that in load control with a constant amplitude fatigue curve with a max stress of 850 megapascal and a stress ratio of 0.1. We were targeting average life of approximately 5 times 10 to the 5th cycles so that we could have manageable fatigue life for all the fatigue samples that were developed by all the partners, and cyclic loading frequency was 10 hertz. All right, so now we're ready to get into the gravy or the good stuff. So here I'm comparing fatigue life distributions that are developed from the stress relief treatment and the HIP treatment. This is, of course, presented here, as you see, for both the vertical and the horizontal orientations. This is a result of metal from 3 different partners. These are presented kernel density estimate distributions. These are just like histograms, and the only difference is what being presented here as a continuous curve rather than individual bar distributions. This makes it easier to compare small nuances of the distributions. And of course, one of the things that I want to point out immediately from left to right in comparing those 2 treatments is, of course, you see the transition of the metal, especially that you see that for the vertical orientation to the right. So that what we get is an increase in the overall fatigue life as a function of HIP treatment. In this case, if we're comparing just averages, it's a little bit over a double, nearly triple the amount of life, average life that's achieved. But the other thing that's very important is you see the anisotropy that's present in the metal, for example, comparing the vertical and the horizontal orientations here in comparison to that which you see that's on the right. So we find that the HIP process substantially reduces the anisotropy between the horizontal and vertical orientations, decreases the emphasis on trying to make sure that we get the orientation correct in a build to produce the highest quality metal for a specific orientation of cyclic stress. You can see that there's a small little bump here in that orientation for the horizontal samples. This is a result of those prior beta grains that are now oriented perpendicular to the axis of cyclic loading and their intersection with the free surface as a result of the build orientation. So small little bump here, but otherwise really great agreement between what we see in responses for those 2 orientations. If we break this down now into individual partner contributions, but now just focus on the vertical orientation response, you can see that in the stress relief condition, we see a relatively broad orientation, broad distribution, I should say, of the actual fatigue lives. And then what we see on the right is you see, at least from what we've been able to develop so far, the distributions agree quite well. You see a narrowing overall in the fatigue lifespan. So we get a reduction in the intra-build variability. And then what we're seeing so far in comparing results of the partners P1 and P2, and P3 is almost finished, that we're also getting a reduction in the degree of inter-machine variability as well after HIT treatment. So we're very happy to see that. All right, we like to many times, looking at fatigue responses, examine the statistical distribution in the data. And so here I'm plotting Weibull distributions for fatigue life responses, the vertical orientation from 3 partners that I had represented earlier. This is for the stress relief condition here, indicating a Weibull modulus and then the shape parameter. And this is a 2-parameter Weibull distribution. So what I'm going to point out here now is the value of doing this is that we could pick out the kinds of defects which contributed to our low life samples, our medium life responses. These are representative, of course, and high life responses. So you're seeing at the low and medium life range 2 examples of void type defects which contributed to failure. And then on the highest end of the fatigue life response, a carbon defect, internal carbon FOB that's actually contributed to failure. These might not be unique from things that you see yourself, but the interesting thing for us, if we do the same now for the HIP treatment, what we saw for the stress relief condition is a very straight line for that Weibull distribution. In this case now for the HIP treatment, we see a little bit of bumps and curves here, which really means typically that there's more than a couple contributions of factors to the fatigue life distribution. So if we pick out again contributions to failure, we see at the low life We have a near surface brittle type microstructural feature, which I'll elaborate more in a little bit, an internal feature, which is relatively similar. And then lastly, up at the high end of life, we see an internal carbon FOD type defect. So the purpose of doing this is to make sure I point out, one, we get an increase, of course, the Weibull modulus, but more importantly is that throughout the fatigue life distribution, we don't see any contribution of voids to fatigue failure. It's all something that's become relieved or become evident as a result of the fact that now all the, the void type factors are repaired. So if I compare those two distributions side by side, I gave you a comparison of the average life distribution, which wasn't that impressive. But if you're looking, for example, at basis numbers, either an A or B basis number, you see that increase in fatigue life approaching nearly a factor of 10 from the stress relief condition, of course, to the hip condition. So very nice response. What I'd like to do, though, is just make sure I point out kinds of things that we see with regards to the major categories of failure origins from fractography. So for the stress relief condition, we saw voids, either gas pores or voids which were largely consistent circular in shape with an aspect ratio close to 1, or we saw much more lack of fusion voids. Carbon FOD, certainly present, and sometimes small bubbles on the boundaries of the individual carbon defects. We saw FOD for an object debris. In this case, that could be an individual particle. You could see in this case, aluminum deficient, higher in carbon. And then also we saw some foreign contamination. We don't call this a FOD yet because you see a region that's aluminum deficient followed by a region that's aluminum rich. And you don't see a discrete particle boundary. You see, for example, an integration of that particular material with the surrounding titanium 6Al4V matrix. So I'd like to point out, first of all, average defect size, understanding those categories. So here what we're using is just some pie charts to represent those 4 categories. And I'm going to break out the voids for the stress relief condition in this pie chart to 5. So show you the percentage of the lack of fusion in the average Murakami dimension of that defect, and then gas pores, and then 3 remaining categories: foreign contaminants, foreign object debris, and then corresponding carbon distinct. You could see that the voids contribute almost 50% to the total number of defects which contributed to fatigue failure. And now if I look on the right, the same pie chart distribution for the hip condition, you see again the lack of fusion and all the pores are gone. No contribution in that space. You see also then our 3 remaining categories: foreign contaminants, foreign object debris, and carbon. But the thing I'd like to point out, which was really surprising to us actually, is that as evidenced on the fracture surface in terms of the Murakami dimension, we actually saw a decrease in the effective diameter of these defects. So we saw about a 20 to 25% decrease in the average defect size from the stress relief condition to the hip condition. So we're still investigating what's contributed to that, what's actually the primary factor which is reducing the size of these anomalies that are contributing to fatigue response. All right. So for those of you that have always been looking for trends between the defects that might be present within the microstructure and then the corresponding performance. So this might be, in this case, cycles to failure. You look on the left, we're plotting here cycles to failure in terms of the Murakami dimension, square root of area. And you see in this particular case that we almost potentially see the start of a relationship here between the lack of fusion and life. But then in the case of the overall data distribution, we don't at all. In the hip treatment condition, we don't see a trend at all. We see also, I point out that the square root of area dimension here is largely less than about 50 micrometers. So reduction overall in size, of course, and no trend. So this is not to be expected. That means a trend between these types of defects depends potentially on location, but also the mechanisms which are responsible for actually the percolation of these defects into a well-defined flaw that results in failure. But it's scary now because you realize that we take away the lack of fusion, which were the easiest things to be able to see in a quality control evaluation, and we're left with these things that are much, much more difficult to see. So important to understand their source and how they're contributing to failures. I drive one more thing home, which is extremely important, and that is one of the major interests for us was the intra-build variability within our machine. So I'm showing you, if you could see on the upper right-hand corner region, a top view of our build layout with zones 1 and 4 near the back of the machine, 0 in the center, and 2 and 3 near the front. And what we're doing is plotting now average fatigue life. This is for the vertical orientation for each of these zones for the 3 partners. This is now in a stress relief condition. So here you're looking at cycles to failure, and you're looking at those individual zones. And I point out these 2 zones, 1 and 4, near the back of the machine that are exhibiting comparatively low fatigue life, significantly lower than you see with regards to the zones 0 and then 2 and 3. So important to recognize for a machine, but not necessarily very desirable, because what you want to do is not have that spatial specificity in terms of performance. What's it caused by? Well, actually, we find also if we superpose defect size within those particular zones, we see we have larger lack of fusion defects which are present in 1 and 4 relative to that in 2 and 3. Examples, of course, are shown here around the periphery. Just some examples in the individual lives that you see for those lack of fusion voids. If we do the same thing now, we do it for the hip condition, we see, first of all, that the average life has increased substantially. As was alluded to before, this again is just distinguished in terms of an average. We also see that there's no distinct spatial difference across those 5 zones. So that treatment homogenized the metal. And again, we show the distribution of some examples of representative defects that were found responsible for the initiation of failure. You can see that none of those are lack of fusion. So we're extremely happy about this, and it's actually increased our efforts to try to understand these major sources and how they propagate into mainstream production. So to summarize, we found that the hip treatment performed according to AMS 7028 resulted in a significant increase in the fatigue life of our grade 5 titanium, both in the horizontal and the vertical orientation build components. The largest benefit was the vertical orientation because it was able to heal those lack of fusion void type defects. After the hip treatment, the finite life fatigue responses of the vertical and horizontal orientations became not significantly different, which was fantastic. The root cause defects in the hip condition are what we found is FOD consisting of carbon source, silicon, tungsten, and then some other small traces of contaminants that we don't have necessarily time to talk about here. But none of the failures in the hip condition actually were attributed to lack of fusion voids. For those of you that are interested in this and you have some similar concerns or efforts, we're recruiting additional partners that are seeking to evaluate their process variability with respect to a growing database, which is hard to develop. So if you're interested, please reach out to me. So Jackson, thank you very much. I think I ran a little bit over, so thank you for being patient with me. If you wanted to.
No, it was great. Zane, I'm gonna think maybe the best option is us just to go through some of these Q&A questions. How's that sound?
Absolutely. And do you want to go ahead and read them out, or do you want me to read them to you and have you answer that way?
Yeah, I can read them out. Dwayne, I think the first question you can speak to comes from Ryan Kircher, and he asked, can you comment on the composition of the non-carbon FC and FOD?
Yeah, great question. So in those 2 categories, we see a variation. Sometimes we see tungsten, sometimes we see silica, and then sometimes we see a mixture with a carbon outline. So it's really varied, and that's why I didn't go into a bunch of detail there, simply because we could go into the subcategories of those individual findings. And it turns out that I'll actually be giving some presentation in this coming conference that comes up in October, the Advanced Manufacturing Conference that will be held. So you'll see more details there.
Great. Dwayne, I'm gonna keep you on the spot while we're talking about this. Tyler Torgerson asked, what was the finished surface finish of the fatigue specimens?
Great question. That was one of the reasons why we recruited Limited Productions, which is here in the Pacific Northwest. They did a longitudinal grind as specified in the standard, and you'll find actually that our roughness was down to 0.2 micrometers. So it was within spec defined by that specific standard. And we had no surface initiation failures from any things that were present at the surface. Great question.
No polish?
That longitudinal grind is a polish. So that was how we were able to get down to that 0.2 micrometers and below. Yeah.
Thank you. Hopefully, Tyler, that answered your questions. Just going to a couple other, I see Matthew Hogan, if you're still on, asking about rapid cooling and quenching affecting the longevity of the hip component. The short answer is no. The Quintus hip units use this wire wind technology and develop it specifically for controlling the pressure applied to the vessel. But this allows for an additional step of this internal cooling channels to get this rapid cooling and quenching. So really the system is designed to do this. It's not like an additional feature that is going to shorten the lifespan of your system. Michael Morwins asked about Inconel 625. Michael, if you're still on here, we haven't done a ton of work recently on 625. We do see quite often 718 in our laboratory, but it's certainly an interest we would have working on if you or anyone else wants to have some comments. Us at Quintus would love to participate in a discussion over it. The last question I have is from G, or at least that I see so far, is how does the microstructure compare between traditional hip and high pressure hip of Ti-6-4 DED versus powder bed fusion? This is a great question. I don't have a ton of experience on it. I would imagine that it's a little less sensitive to the temperature segment than powder bed fusion is. But this is certainly something, if you want to reach out to me, I'd be happy to dig in my resources pocket and get you a more firm answer than that. Dwayne, can you see the Q&A?
I think I could see it. This in the Q&A, I'm looking here.
Yeah, and we just had 2 new questions come in as well.
I can read
Okay,
them
I
to
see
you.
one from Jessica. Is that right? Is that what you're referring to?
Yes.
Okay. Jessica asked, how did the team control loading in the stress relieving a hip condition? Was everything kept on the plate? Actually, to be able to reduce shipping efforts between the partners, the individual groups or clusters of specimens were sectioned from the plate, and then they were heat treated, combined in those particular clusters. Yeah, but we heat treated all of the clusters for each partner together. That means contained as if it came off the build plate, but the individual build plate sections were removed. And there was no other material that was present in the runs with regards to the metal that was produced here in our program.
Dwayne, another question I see. So you're doing powder bed fusion of Ti-6-4 on an EOS. Are you ever interested in a different OEM besides EOS for this work?
Yeah, definitely. What I showed you is what we refer to as the inner core partner contribution. The inner core was a contribution from someone that's operating an EOS M290. But we're also interested in adding additional partners from an outer core. So that means a variation that could include their own machine and or a specific powder that they'd want to compare with regards to the variability that they see that came from the effort that we conducted, of course, with a single controlled source of powder. So definitely, if you have interest in that, please reach out to me.
That's great. Dwayne, if you're okay, I keep seeing some pop up for you, so I'll keep reading if that sounds good.
I see one here from Ryan. Is that one here?
Yes.
Okay, I see from Ryan asked, do you have any hypothesis on the cause of locations 1 and 4 having more lack of fusion in the stress release specimens? Definitely. We have a compatible study that's going on with evaluating the gas flow distribution within the EOS M290. That effort resulted in a paper that just was published in additive manufacturing, and it shows what we find in terms of some gas flow variations and differences in those zones with regards to the other. So I'll leave it at that. Hopefully I'll get everybody to read that paper and take a look. You can see this is something that has been talked about in industry, of course, the influence of gas flow variations, and whether the flow is laminar or turbulent, and it's a potential cause here for sure. Nice to see, though, that the HIP treatment is able to overcome that. I have, and this was, I guess, what you read to me. Can you comment on the composition of the non-carbon FC and FOD? Yeah, and yes. So I commented on that already.
I believe you did. Yes, I see some in the chat that I'll read to you. Did you investigate any lower loads, such as 10 to the 6, 10 to the 7 cycle range? Typically much more variability there versus 10 to the 5 cycle.
Sure. The person is exactly correct, and that is that there is typically more variability at that higher life average. We're not conducting that here, of course, and the reason was so we could get through the volume of metal that increased the power of our statistical comparisons. But it is part of our program overall that we're conducting cyclic loading at some of those lower stress amplitudes in order to be able to see if we percolate different families of root causes or defects. And so, great question. And we're doing that. Hopefully, if that's of interest to you, you reach out and we'll talk a little bit about that.
Thank you. I see another question from Amir. I'll read it and see if we can answer it. Any reason why lack of fusion pore structure was printed and tested, then compared with HIP samples? Does that?
Any reason that lack of fusion was printed and tested? It was to be able to retain the microstructure that would be in the printed condition and then that would receive a stress relief only, because there are some applications where a HIP cycle might not be desired. And the question was, what would be the penalty in the performance of that metal relative to the HIP process if it wasn't subjected to a HIP treatment? And so that's the reason why we would go ahead and conduct that cyclic loading evaluation in the stress relief condition, is to really have that data available, because the partners that we were working with really wanted that as well. That was important for their business case decisions.
Yeah, great question. Thank you, Dwayne. I have a couple more for you. I'm seeing Ryan asked the SR histograms indicate one of the participants seemed to have a lower performance. Were there more bigger defects in these specimens, or do you know the reason why this, what caused this?
So we do have some information regarding, this was in the SR condition, and not all machines had exactly the same pore distributions in that condition. And so indeed, we did find that there was some relationship or connectivity between the size of the pores that were present there and the corresponding fatigue life. But I can't go into the additional details here, just simply because, a lot more to discuss.
Of course, of course. Do you have any plans for high temperature fatigue testing, or is that kind of outside the scope of this?
Yeah, well, great question. We have a lot in front of us in terms of conducting room temperature type evaluations. High temperature might be in the future. We could always be encouraged to conduct high temperature if someone was really interested in that. So at present, we haven't thought about doing that.
Perfect. Dwayne, that's all the questions I can track down at the moment. I don't know if Zane, do you see any more?
We just got one more in, but yeah, so we're coming up on the top of the hour, so we've got 4 minutes left. If you have any other final questions, go ahead and submit them in the chat or the Q&A section, and Jackson and Dwayne should be able to address as many as we can, and then once we get to the top of the hour, we'll ask that you reach out directly via email to Jackson or Dwayne via their emails there on that last slide to continue that conversation.
Yeah, Dwayne, I see some more questions pop up for you. Do you have a plan to look at different R ratios?
Yeah, another great question. And wow, fatigue just continues to grow and grow and grow in terms of the potential influence of parameters. So we have not discussed that in detail, and the reason is because we're still trying to build the database with the standard, R is equal to 0.1. It can be something that comes up, I think, in the future, but at present we found that the majority of the data that people want in order to be able to compare their machine in comparison to those of the other partners and the growing database is to actually develop in 0.1. But again, same thing that was pointed out with regards to higher fatigue lives is that the difference in stress ratios can percolate generation of other defects contributing to failure. So it is something that would be worthwhile to discuss and evaluate.
That's great.
Please
Thank
reach
you.
out to me, I'll say.
I see a question from Sando. Could you maybe explain the difference in absolute Murakami dimensions causing failure? And can this be explained by the difference in microstructure coarsening?
Wow. Well, the coarsening that we see in the microstructure is at a size scale. That means those individual alpha and beta components, which are a couple of micrometers on average maximum, is a factor of magnitude smaller than we see as the Murakami dimension for the defects that we find on the fracture surface. So we have not looked at that. But it could be something that would be worthwhile to pursue. So yeah, great question, and I'm not sure I pick it up 100%, but still, would take a look.
All right,
that's about all. I will quickly say, if you've made it this far, thank you for sticking with us for an hour. I know Dwayne and I would both encourage questions and emails to what you see here. And as mentioned, we at Quintus here love to collaborate and work with universities, national labs, and OEMs to develop HIP work. Some of this conversation that Dwayne has addressed, Chad and I have been a part of and are very grateful to support that effort.
As we are very thankful for you being supportive. Yeah.
So with that, let's squeeze one more question. See that popped up. Can you distinguish the carbon contamination between that? Can you distinguish the carbon contamination between that comes from the build versus from the SEM beam?
Yeah, great question. So yes, we can. We've seen the carbon defects lodged within the metal. And so we know that the source is actually a part of the build environment, and it's easy to be able to see from the morphology of what carbon might be put down as a result of the SEM chamber. So we've been able to distinguish them quite clearly.
Thank you.
Yep,
Awesome.
my pleasure.
So, yeah, with that, we are at the top of the hour, and I am going to mispronounce your name. My apologies, Oluwasiai. If you go to this link, you'll be able to find the presentation recording there here in the next couple of days. And if anybody else has any questions, please reach out to Dwayne or Jackson or myself, and I will be happy to connect you, or Jackson and Dwayne would definitely be happy to continue that conversation. So thank you all for joining today, and I hope everybody has a good rest of your week.
Thank you.
Thank you, everybody.